So we are essentially concerned with this tiny bit of matter there. Okay? So if you are really ambitious, you should go there, trying to understand that thing that is not well known. And so actually we are even less ambitious than that. Okay, we are very shy, very humble, and what we want to understand actually is the proton mass. Okay, if we understand the proton mass, we will be happy, and we can retire. Okay, so this has to do with quarks and gluons. Okay, at that level, we want to understand where the mass comes. Okay? Because we have electrons that we see, we have also neutrinos that we can kind of detect in the laboratory, okay? But the fraction of the masses of electrons, neutrinos, and other particles is very tiny compared to the mass that is in the atoms or in the atomic nucleus. Okay, that's the reason. Once we understand the proton, then we can claim we understand the rest. Okay. So before I go on, this has nothing to do with God's particle. Okay. Probably you have heard about that, right? The God's particle. This has to do, where is it? Oh, it should appear something, you cannot see it. It's there. So it has nothing to do with the Higgs mechanism or with the Higgs particle, okay? So the proton mass comes from somewhere else. It doesn't come from the Higgs. And that is extremely important to understand that. And I want to convince you or try to show how we understand or we want to understand where the proton mass comes and why we are saying it doesn't come from the Higgs. You must have read in newspapers or elsewhere that the big deal about the Higgs because it explains the mass of all particles in the universe. This is not the case. Okay, this is wrong. This is just to repeat what I'm trying to say, is that more than 90% of the visible matter is made of protons and neutrons. When I say visible, I mean that it interacts with the electromagnetism, okay, such that we can see. Okay. And so I will discuss saying that if you take this picture here, says that the proton is made out of 3 quarks. Okay? But if you take the masses of these 3 quarks, okay, you add them up, this gives only 2% of the proton mass. So each of those particles there, the quarks, they have a mass. But it's very tiny. Okay, in units that we like to use is 2-3 MeV. Okay? So the electron mass is 0.5 MeV. Certo? Okay? The quarks have of the order of 3 to 5 MeV. If you add up these 3 quark masses, it gives 15 MeV. Okay? But the proton mass is 930 MeV. So just adding up the masses of the 3 quarks doesn't account for the proton mass. Okay? Now, if you take, say, the masses of the electrons plus the masses of the protons and the neutrons, this essentially gives the mass of an atom. There is a tiny difference because of the binding energy. Okay? But essentially, if you sum up the masses of the protons, the neutrons, and the electrons, you get the masses of the atoms. If you want to play the same game here, it doesn't work. It doesn't come from the quark masses. Now, the quark masses, they do come from the Higgs mechanism, from the Higgs particle. Okay? So the quark has that mass of 3 to 5 MeV because of the Higgs. Okay? I will not talk about the Higgs. I don't find it interesting. So the remaining 98% must come from somewhere else. So it comes from the gluons, and that I will try to show you how. So the starting point for us to understand where this mass comes from, it seems, is this QCD. QCD is quantum chromodynamics. I want to explain you what theory is that one. Okay? So why are we convinced that that theory is correct? You might have heard about this scientific journal called Science. Okay, it's very difficult and very expensive to publish there. Okay, it's only very fundamental discoveries are published there, or important developments. Okay, and essentially what comes out there should be true. Okay. So this is a calculation of the masses of these particles that interact strongly. Okay. So QCD is the theory that describes these strong interactions. Those particles here, the proton, these are mesons here, pions, kaons. Here is the nucleon. Here is the proton and the neutron. Okay. So this is a calculation from the fundamental theory from QCD. Okay? So starting from QCD, we derive these masses here. Not we, I mean these people that have done the calculation. Okay? Even more impressive, another paper in Science must be true, is the difference between the mass of the proton and the neutron. You know, the mass of the proton is 938, of the neutron is 939 MeV. The difference is of the order of 1 MeV. Okay? Where this mass difference comes from two effects, from the masses of the quarks, the composition of the neutron and the proton is different. Okay? The proton has 2 U quarks and 1 D quark, and the neutron has 2 D quarks and 1 U quark. They have different masses, so this gives a difference in that mass. And also because of electromagnetism, because the proton is charged, and this gives also a contribution to the mass. Okay? This was calculated, okay? So these things here, these are the predictions, these are the calculations, this is experiment, and this is the red dots are the calculations. Okay? Derived from this fundamental theory that I want to explain you what it is. How did they compute that? They compute it with supercomputers. Okay? This is a blue gene. Okay? I think Brazil has 1 supercomputer, but I cannot turn it on. We don't have money to refrigerate it. Okay? The water that we need to refrigerate such a computer, the electricity is so expensive that we cannot pay it. Okay? So we have one there in Petrópolis, not a blue gene, another one, and we cannot turn it on because it's too expensive. It's not a joke. Okay? QCD, so it's quantum chromodynamics. This is the theory of this strong interaction or this strong force. Okay? So what systems interact through this strong force? Quarks and gluons and their bound states. So what are quarks? Quarks are like electrons. They are spin 1/2 particles. Gluons are like photons. They are spin 1 particles. Okay, I will talk a little bit more about their properties. What are the bound states? Bound states are baryons, like the proton, like the neutron, and other particles. Okay, there are many of those. So these are bound states, like an atom is a bound state. It's bound by the electromagnetic force. These particles are made out of quarks and gluons and are bound by the QCD force. Okay? Then you have the mesons. The mesons are the pi meson, okay? Discovered by Cesar Lattice, our great hero. Okay? Then you have others like the rho and d. Okay? What is the difference between baryons and up to the end I will manage. Okay, so don't worry. Baryons have spin 1/2, 3/2, 5/2. Mesons have spin 0, spin 1, spin 2, perhaps. Okay? Another bound state is at the atomic nucleus. Okay? Atomic nucleus is, at the end of the day, is made out of quarks and gluons. Okay? Because they are inside protons and neutrons. So at the end of the day, they are bound states of quarks and gluons. Okay? Also super dense stellar objects, those that result, for example, from supernovae explosions, neutron stars, okay, or quark matter. You have a neutron star. At the center of a neutron star, you can have only quarks. Probably you have seen this. I'm showing that just to give you a scale of dimensions that I'm talking about. So you have the atom here. Here's an electron. Here's the nucleus. Here are protons and neutrons. Okay, and here are the quarks. Okay? So what is if this is the hydrogen atom, say, okay, it's not the hydrogen atom because you have more protons and neutrons. Suppose a helium here, okay? You have, what is the distance between the center here to the electron, more or less? You must know that. What is the distance of the electron on average in an atom? An angstrom, half an angstrom, 10 to minus 10 meters. What is the distance, what is the size of the nucleus? 10 minus 15 meters, okay? Can be 10 times 10 minus 15, okay? So you have something here, then you have the electron there, okay? This is of the order of 10 minus 10 meters, 1 angstrom, and here is 10 minus 15 meters, each one Fermi. Okay, so the ratio of this to that, how much is it? $100,000. If this is, say, 10 centimeters, just to make this scale, this is 10 centimeters. So what will be this difference is here? 10 kilometers. Okay? So if this is the size of the nucleus, the electron will be 10 kilometers from here, Avenida Paulista, beyond Avenida Paulista. So I'm going to talk to you about things that happen here inside. Inside the proton, inside the neutron. Okay? So the electron is out there. Okay? Got the picture, what I'm talking about? This is the atom. I'm talking about particles that are inside the nucleus. So this is the standard model. These are the elementary particles, okay? Those that get the masses from the Higgs, okay? Although the neutrino is massless in the standard model, today there is evidence that the neutrino has a mass, but this is beyond standard model. And here are the quarks. Today we know of 6 quarks. Up and down, up and down. This is 3 MeV, this is 6 MeV, this is 1.3 GeV, okay? So you see you have different quarks here, but those that make up the visible matter are these ones. Those make up the proton and the neutron. These ones make up other particles. Okay, they are not stable, they decay. Once they are produced in an accelerator, cosmic rays, or at the origin of the universe, they form bound states and then they decay. Okay? They decay to the lighter quarks. Okay? So I'm talking about these quarks here. These are the quarks that make up the nucleus. This is just to say you about the bosons at the most elementary. This is the photon, okay? These are the W. These are responsible for the weak force. When the neutron decays, it decays not because of electromagnetism or because of the strong interaction. It decays because of the weak interaction. Okay? The photon is responsible for the force between 2 electrons, an electron and a proton, for example. Okay? So these weak bosons are like photons, but they have masses. Okay? And the masses, all this thing here comes from the Higgs physics and all that. Okay? That I'm not going to talk about. It's so irrelevant for us that I will not spend time. But then you have the gluon. Gluon is like the photon, but it is related to this strong interaction. Okay? If you have questions, please ask. So where QCD is important? QCD is important, first of all, at the origin of the universe when you have here you have the Big Bang, and then you have this kind of a rapid expansion here, the inflation. Eventually, you will have recombinations. So this is a soup of quarks, electrons, and neutrinos, photons, and then this expands, cools down, and then you can create, say, the first mesons and baryons. So QCD is relevant in this region here when you have quarks and gluons starting to combine, okay? In the nucleosynthesis, primordial nucleosynthesis. And then you get formation of hadrons, because then you combine protons and neutrons, you form protons, you form nuclei, and then you form atoms, and then you form stars, and eventually these guys here are formed too, okay? So QCD is relevant in many parts here. In the evolution of the universe is here, and then also here in the physics of the atomic nucleus, and then also in superdense matter. This is just a nice picture of a pulsar. Inside that object is the same object seen in different wavelengths. Okay, visible, and one of this is X-rays. I don't know which one, but I only know that this is visible. And inside here there is a neutron star. That we believe that inside the neutron star you have essentially neutrons or quark matter. QCD seems to be relevant for the question of dark matter as well, okay? Because I don't have time to talk about actions, but has is some remnant of QCD, okay? So QCD might play a role for dark matter as well. Now I have to explain you what is QCD, okay? So QCD, quantum chromodynamics, and the name comes from the analogy with quantum electrodynamics. Quantum electrodynamics is Maxwell's equations, okay? This is responsible for everything here in this room, comes from electromagnetism and gravitational physics, okay? If there's no gravity, we were being here fluctuating, okay? But we are made up by atoms and molecules and a combination of them that comes from quantum electrodynamics, okay? Here, the key role is played by the electric charge, okay? In QCD, also there is a charge, but is not electric. It's a different name. It's called color. And I will explain you why is it, what is this charge? What is color charge, okay? So in the next few minutes, I'll try to explain you how we understand charge. What is charge? Okay? It has to do with symmetries. Okay? So this is really for undergrads now. Okay? If you want, if the elder want to go out for a coffee, they can go. Okay? I want to get to the concept of a charge. This will take me 5 slides. Okay? Let's start with something that eventually you know, which are the Maxwell equations. In free space, no charges around. So you are in a region, you have only electric and magnetic fields. They depend on time and position. Their movement is described by Maxwell's equations. Okay? They are equivalent to this. I replace one in the other here, use those, and I get is the wave equation. What is that? Electromagnetic waves. Okay? The energy carried by such an electromagnetic wave is E squared plus B squared, the integral of the space that you are considering. So keep that in mind. This must be kind of familiar to almost everyone here, okay, if you are not at the very beginning of undergrad, okay, Maxwell's equation. So there's Coulomb law, Biot-Savart law, and all this stuff, okay. This is classical. Now we have to include quantum mechanics, okay. Quantum mechanics usually is not done with the E and B fields. You introduce auxiliary quantities, say vector fields and scalar fields. These are the potentials, okay? Vector potential and the scalar potential, okay? In vacuum, it's convenient to work only with A. The other one is you can get rid of, okay? And then instead of E and B, you use a single A function, and you get, again, a wave equation for this quantity. That is not E, neither B, but you can get E and B from that, okay? And then this is also a wave equation, okay? Now let's make a Fourier expansion. Let's expand this A in terms of a Fourier series. Put this inside there. This is all classical physics, okay? There's nothing quantum yet, okay? So take this, put it there, okay? And then you see here this second derivative with respect to time, okay? Will bring omega square, k square, dA, this is Laplacian, will bring this k square here, okay? And then you get this equation here. Okay, here is k squared. Again, is an equation, okay, for the A in time now space is kind of simple, okay? And this is, you see this, right? Take this, put it there, you get this thing here, okay? So what is that? Second derivative of a quantity equal to some, of course I put omega there just to already give you a hint what is that, times A, okay? So it's something like x plus omega squared x. If you don't like A, you can use x. Okay? Then gives that equation. Okay? So what's that? The harmonic oscillator. Okay? So the Fourier components, they have an harmonic motion. But now if I want to quantize the harmonic oscillator, this you do in undergrad, master, PhD. You solve the harmonic oscillator once a week, okay? You must know this, okay? How to quantize the harmonic oscillator. I have discovered that the amplitudes of the waves, they are harmonic oscillators. So I will quantize them, okay? And to do that, I use that famous ladder operators, creation and annihilation operators. Operadores escadinhas, okay? Once I do that, okay, I will skip now all this because it's so boring. You know this so well that I will skip it. But let me tell you, when I do this operation here, expand in creation and annihilation operators are this A dagger. Remember, X you can write as A plus A dagger, and X dot, which is momentum, A minus A dagger. Okay? You put it back into the expression of the energy, and you get what? You get that the energy is a sum of energy packages because the energy is quantized, okay? This lambda appears here because you have polarization, but don't worry, this is irrelevant. What is relevant is that the energy carried by this electromagnetic wave in quantum mechanics is quantized. And these packages of energy equal to h bar omega, remember omega, k squared, c squared, omega squared, okay, is a function of the momentum. Each Fourier component, okay, has an energy associated with that, and is h bar omega, proportional to h bar omega, okay? And these are what we call the quanta. And the interpretation is that these quanta, these packages, these particles are the photons, okay? So the photons are what? Are these packages of energy that make up an electromagnetic wave, okay? So the quanta are the carriers of the energy, and momentum, angular momentum, and all that. Okay, so photons are particles that make up the... If you have matter, this was for radiation, this was for electromagnetism. Now, if you have matter, this you must know too. You have the Schrödinger equation, how you quantize classical physics. You take the energy, let's do it for the free particle. You take the energy, p squared, you take the energy, p squared over 2m, and put a hat on p, okay? And say that this hat means is that derivative there. Replace it back and multiply by a function of x and t, okay? This is Schrödinger's equation. If you have an interaction, you have to put there the energy is given by kinetic energy plus potential and you do nothing with the potential, simply add it there, you get a Schrödinger equation. Then if you have the Coulomb potential, you get a hydrogen atom. Once you got the hydrogen atom, you get everything, okay? Because it's just a complication now. And this complication is called atomic physics, molecular physics, condensed matter physics, and all that comes from there, okay? And there you get a continuity equation, a conservation law. You must know that, conservation of probability, okay, that comes from the Schrödinger equation. This is valid not only for the free particle. The potential cancels here. You have plus V here, the potential is Hermitian, if it is real, it cancels, and then you have a conservation law. What is conserved here? What is conserved is the probability, okay? If the particle is sometime here, it must be found somewhere else. It cannot disappear, okay? Relativity, let's complicate a little bit, right? You are here because of relativity, not because of non-relativistic physics, right? So relativity, the relation is E squared, the energy. Before was P squared over 2m. Now, in relativity, this is the expression. Play the same game. Schrödinger played this game. Before his equation, actually, he had this one that I wrote down there. Only later he wrote for the non-relativistic, but first he got this one. Take this, put a hat there, okay, and this must be an I, square root of -1, okay. And again, you get a conservation law, precisely here. So the equation you get instead of Schrödinger equations, you get what is called the Klein-Gordon equation, okay? This will be then the equivalent of the Schrödinger equation for relativistic particles. That's a problem. Always you have problems. Never things are easy. So you have the continuity equation. You can derive it from here. Even if you have a potential there, you can put plus some force, some potential. This is still, you have the current like before, but this rho that before was psi star psi, now is not anymore. Now it's more complicated. You see here, is not always positive. So this cannot be a probability, cannot be a probability density. Probabilities are positive. You cannot have, only in the lottery you have chance of minus. You never will win, but some people win. And then, this cannot be good. Okay, this cannot be a relativistic wave equation to describe particles, okay? But it doesn't mean that this equation is useless. What you do, you treat this wave function like the photon, like the E and B functions we had before. You think that phi here is actually a field, okay? Not a wave function, not a wave function. You think that this is a field. Once I quantize, what will happen? That equation here, you make the Fourier transform, play exactly the same game, what will you get? Harmonic oscillator. This thing also oscillates. But the frequency, the energy, has the mass there. Essentially reproduces that equation there. So the quanta of that field are objects that carry energy, momentum, and mass according to that expression here, p squared plus m squared, okay? So what is a particle? It's the quantum of a matter field, okay? Quarks, what is electron? Electron is a matter field, okay, whose quanta the electrons are, okay? This is the way we think of particles. Particles are quanta of fields, like photons are quanta of the electromagnetic field, and then you have matter fields. Once you quantize, you get this interpretation. Good. I'm not there yet to tell you what is a charge, okay? So where conservation laws come from? okay, come from symmetries. You can have also conservation laws that are not related to symmetries, but let's concentrate here only on symmetries. So symmetry implies in a conservation law, and usually a conservation law implies a symmetry. One very familiar one is if you have an harmonic, if you have a Hamiltonian like that, p squared over 2m, r is the modulus of the vector r. The Hamiltonian is spherical symmetric, is invariant under rotations, and the consequence of that is that H commutes with L, where L is given by R dot P. What is R dot R cross P? Is the angular momentum. So if you have a spherical symmetric Hamiltonian, force field, spherically symmetric, it means that the Hamiltonian commutes with L. Consequence, dl dt is equal to 0. Where did I get it? From the Heisenberg's equation for an operator. And then if this is 0, then dl dt is 0. Angular momentum is conserved, doesn't change in time. Okay? If you have a particle under a central field of force, it evolves, but its angular momentum doesn't change in time. Okay? You must break the rotational symmetry for the angular momentum to change. That is the meaning of the conservation law. Okay? It comes from the spherical symmetry. And there is a consequence. It's not only, okay, fine, big deal. No, it has a consequence. It has the degeneracy in the energy spectrum. Take the hydrogen atom, Coulomb field. You have the ground state, excited state. Well, the excited state actually are three states, three wave functions for the same energy. This means degeneracy. That state is degenerate because of the rotational symmetry. If you put a magnetic field on the top of the thing, this breaks rotational symmetry. And then these three levels will open up. Okay? Now to go faster, I have to introduce some notation. This is nothing, okay? It's just a symbol. Delta x med, that, and x0 is time, okay? Xi is the usual coordinate, and so we write this in a compact notation. It's just to have equations more compact. Every time you see this thing here, it means derivative. Don't pay attention if the symbol is up or down. There are some people that make a big deal about that, okay? And many students have to master that, okay? Otherwise, they fail in courses if they don't know how to bring this to that one, okay? Feynman did not like it, okay? He used every symbols, although he complicated the definition of x0, okay? In this notation, our Klein-Gordon equation is just that, a box, M, this should be M, okay? It's M0 from my old transparency. So this was Klein-Gordon's equations I had before, and now it becomes like that, and that thing here is a box. So this is the Klein-Gordon equation, and the continuity equation is just that, you see? This means conservation of the current. Okay? These are four vectors. Some of you must have seen it under undergrad if you are in the last year of your undergrad. This is the covariant notation. It's just to simplify notation, okay? Because I have to go fast now, okay? And then this will be helpful for me, okay? So okay, this is just notation, fine. Now I'm making a statement for you. The Klein-Gordon equation can be derived from a least action principle. Newton's law and others, they can be derived from a least action principle. Okay? Those that have made analytical mechanics know what I'm talking about. Okay? The action is the integral of the Lagrangian. Okay, I'm talking about fields now. Okay, fields are like coordinates, but it's like the electric and magnetic fields. Okay, and the Lagrangian is given by, you see this fancy notation here? This is simply derivatives, so don't pay much attention. Okay, and the Euler-Lagrange equations that you get from there are given by that. So you can derive the Klein-Gordon equation by an action principle. You require that variation. This is all classical physics. Once you quantize this now, you get the interpretation that the quanta of these fields are particles. Maxwell equations can also be derived from a least action principle. The Lagrangian density now is given by that. F min E is given by that, where the mu, these things are the electric field, magnetic field, and so on. So this short notation here is for this thing here. Okay, it's just a notation. It's simply to simplify notation. But will be helpful. Interactions. So far, I have not put interactions between the fields. Okay? So far, I have in my Lagrangian only phi times phi, or phi star times phi. Okay? Now I have to put interactions. You see, interactions involve 4 fields. You must have phi, 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 phi. What is the interpretation here? You have one field for one particle, for another particle, they interact, and other particle come out. You need 4 fields. This is one of the fields, and so on. This gives you only propagation. It comes from this point to this point. Okay, you create a particle here, and you annihilate here. You create one here, another one here, and then you annihilate here, and they appear there. So for having an interaction, you need to have 4 fields. If you want to describe a decay, you need 3 particles, 3 fields. You have 1 particle, and then it decays, and so on and so forth. Okay? So interactions are given by products of fields, like those here. Okay? So recall, free particles, only 2 fields. Interactions, 4 fields. Symmetries. Now let's try to get to the charge, concept of charge. Take a phi that appears in the Lagrangian and make a transformation. You like the angular momentum thing. If this is rotational invariant, you take r, goes to a different r through an angle theta. The Hamiltonian doesn't change. Let's see what happens if I make this transformation here on the fields. What happens? Instead of phi, I will put phi prime. So L goes to L prime. You see here? You have the free part plus the interactions. Because this is e to the minus IE, and this is plus, this cancels out here in the product. Phi star times phi, they cancel out. And the Lagrangian is invariant. Lagrangian is like Hamiltonian, okay? So the Hamiltonian being invariant under a symmetry, what symmetry? Rotation, implies a conservation law. A Lagrangian invariant under a transformation implies into a conservation law. This is Netter's theorem. Those that have made quantum field theory 1 or classical physics, this is all classical. You have conservation of, this is the continuity equation, and this is the current, and then the interpretation is that the integral over the zeroth component of that current that is conserved is the charge, is the rho. Okay? So what is charge? It's a consequence from a conservation law. Charge is conserved, is given by this, okay? Because of that, you have the key dt doesn't change in time. Okay? So this is a generic name, charge. We call it charge. Once I apply it to electromagnetism, okay, if I involve now photons and electrons, this what appears here is precisely the electric charge. Okay? So charge, conservation of charge, is consequence of this symmetry here, which is called a gauge transformation. Okay? Fine. We are theoretical physicists. We like to play now. We like to complicate things. Alpha was a constant there. Now suppose alpha is a function of t. Alpha is this thing here. Is this transformation here. This was a constant here. Okay? Simple number. Now, suppose alpha is a function of t and x. Then we have a problem. Why? Because when I want to transform the derivative here, it will pick up the derivative of alpha. You see up there? Because alpha now is a function of x and t. So the derivative will pick up that thing here. So once I multiply this by the complex conjugated, this term remains there. It's not invariant. Okay, so a dumb idea, right? Why complicate? We already know what is a charge, it's conserved and happy. No, but let's play a little bit. I don't have anything else to do. So let's complicate that. So this is not invariant. There seems there is no conservation law. No, but we can fix it. Okay, we can fix it. How? We introduce a new field. Okay, we had only phi. Now, so we introduce another field such that is compensated. Okay, we instead of the derivative, we started with our Lagrangian. Our Lagrangian had the mu phi here. Now, don't start from here. Start from here. Where that d mu contains this extra field here. I call it A. Okay? Let's start from there and call this capital D. And require that when I make that change in the phi, this A also changes. So phi doesn't, if I change phi, it doesn't leave this invariant. I introduce another field that when I transform phi, A must be transformed as well. Okay? Such a way, you see here, it enters with the mu. Of course, I postulated that. Why? To cancel that one thing here. Okay? Because now, what will happen? I have to consider this. Now, not this. This is over. I'm here now. Okay? So I have, then what happens? I have to transform phi and A, but it transforms then in this way. We are back now. Everything works like in the beginning here. This will transform e to the I. Now this object here transforms e to the I. You see here? If I multiply both complex conjugated and that, this is invariant now. I can get a new theory with two fields now. I have the phi field and the A field. And through these transformations, I get an invariant Lagrangian. But this is a local gauge transformation because the transformation involves an alpha that is local. Okay? Fine. But you see, then you get interaction now because this d mu gets interaction. Just demanding invariance under a symmetry, I get interactions between matter and this phi. I have phi and I have A now. They are interacting. The interactions come because I want to insist in symmetries. Okay? Now, things get a little bit more sophisticated. Okay, I have to give a dynamics to this A field. Okay, must have a free part. I only have, that symmetry only gives me a interaction, but it has to have a free part as well. Okay, and at the end of the day, I get a Lagrangian that is given by that. This is invariant under local gauge transformation, and the current is still conserved because of that symmetry. So what is charge? Charge is the integral of the zeroth component of a current that is conserved. Okay? So electrons carry electric charge. Quarks carry a charge as well, but it's a charge of another kind, because from experiment, I know that quarks appear in 3 species, not only one. I need 3 fields there. And if I want to transform these fields now, I need to write e to the I, but to mix 1, 2, 3 here, this must be a matrix, a 3 by 3 matrix. So I have 3 quarks, and I want to transform them like I transformed with phi, and then I need a 3 by 3 matrix, and this 3 by 3 matrix I can parameterize in terms of these other matrices that are called the Kalman matrix, and now things become, okay, quantum field theory, and you must come here to learn this, okay? So quarks appear in 3 species. How do I get this from? From experiment, believe me, okay? But you see here, to get the theory invariant now, I need 8 parameters. So to fix this, 8 parameters requires 8 matter fields. 8 matter fields. 3 vector fields. For the previous case, only 1 field, the photon, A. Only one field. Now I need 8 fields. These are the gluons. Okay? So quarks are matter fields. They appear in 3. For having a theory that is invariant under this transformation, I need 8 fields, and these 8 fields are the gluons. Okay? And there is a charge associated with this gauge transformation, and this charge will give the name of color. Since I have 3 quarks, I have 3 colors. Okay? 3 charges. And we call them red, green, and blue. Okay? But it has nothing to do with color, actually. Okay? It's like positive charge, and positive in a little bit, negative a little bit. So it's red, green, and blue. Okay? There is a reason for that. Okay? I will not tell you. But there is a complication now. Instead, electromagnetism will be, Maxwell equations come only from this. But now there is an interaction between the A fields. A photon cannot interact with another photon directly. If you have a photon and another photon, how can you get a photon there? There is no direct interaction. You have to have matter here. Okay? Now, there you have F min E times F min E will give, for example, a gluon interacting with another gluon, another gluon, another gluon. Directly, you don't need quarks there. Of course, you can also have this, and this. But this is new. This is self-interaction. You can also have 2 gluons, another gluon, another gluon. Okay, this is new. This electromagnetism doesn't have. Okay, and this is the main difference between QED and QCD. You have the photons there, and you have the gluons. But the gluons also carry color, also carry charge. It's like having photons with charge. Okay? So this is the picture of a proton. You have these 3 quarks here. okay? One quark, red, green, and blue, and this is the interaction, okay? Don't pay attention why you have strings there. Effects of gluon self-interactions. There is one property that is called asymptotic freedom. Means, I will talk about. You have color confinement, and you have mass generation. So my seminar, we will start now, is mass generation, okay? So asymptotic freedom means when you have a very short distance, the interaction is almost zero. When you have an electron going very close to an electron, the interaction grows in QED. In QCD, it decreases, okay? Confinement. Confinement means what? No one has seen a quark or a gluon, okay, in the laboratory, in a detector. And why we have not seen it? Because we believe QCD confines this property called color. Okay, this charge, you cannot detect it directly in the laboratory. It's confined. Okay, and the idea is that you have a quark here, another quark here, and when you pull them apart, the interaction grows. It grows until it has a lot of energy here, and then it breaks in a quark-antiquark again. They are never free. Okay? Confinement is believed to be that. If you have only poor gauge, you don't have matter, you have only these interactions here, this comes out from a computer simulation. You actually see here, you have a charge here, a color charge here, another one here. In the middle, you have a flux tube. This is string. Okay? Now, once you have quarks, okay, you don't see anything there anymore, okay, between them. You see that? You have here, you pull them apart. There's no color flux in there. Why? Because it broke, okay? This antiquark and quark here in the middle, they join here, and this gives another meson, say. Okay? Flux tube, this idea of having a string, has no place in QCD. Okay? There are no strings. If you hear someone talking about strings, in QCD, they don't exist. Okay? So what is confinement? It's not through strings. Okay, we here at the IFT, we are working on this dramatic change in analytic structure of quark-gluon correlation function, meaning that these quarks actually have complex masses and they cannot propagate. And also we are starting to look at quantum entanglement to see if we can make sense of confinement with this notion of proximity and cluster decomposition. These are very technical things, okay? You look at Google, you will find these things, okay? Mass generation, this is my seminar. I will start it now, okay? This is because science paper, computers, okay? They compute it in a certain way, okay? If you look up my transparency, you will find out how they compute the masses, okay? So what we want to know is how precisely those numbers come out from the QCD Lagrangian. One thing is getting them from experiment or from a computer simulation. You get the numbers, you know this is correct, but you don't understand what is happening. So our aim is to understand where this mass comes from, okay? This is almost at the end. I know the organizers are getting nervous, okay? This is almost the end, okay? It comes from something that is called an anomaly. I have spent a lot of time here talking about conservation laws. So all that derivations that I have done, this is at the classical level. Okay, when you have the current conservation, okay, it is because of some symmetry. This happens at the classical level. The classical field equations obey that. Once you quantize the theory, that current is not conserved anymore. Okay, and this is called an anomaly. Here in QCD, the relevant anomaly to understand that is, okay, you have the heavy quarks. For the proton and the neutron, they are completely irrelevant. Forget them. Put it infinite. and the others are very light, put them equal to 0. So this is a limit, just understand. Okay? The light quarks you put equal to 0, and the heavy quarks you put infinite. QCD has a symmetry, which is this scale symmetry. You take x, multiply it. X is time and position. Multiply by a lambda, a scale transformation. Okay? The QCD Lagrangian is invariant. The QCD action is invariant under this transformation. There must be a conservation law at the classical level. There must be a conservation law. Okay? It exists. It's called the dilatation current. Okay? What is the consequence of this symmetry? Is that all masses should be 0. All hadron masses should be 0 if this is correct. Because this conservation law. This conservation law, you can relate it to the energy momentum tensor. The expectation value of the energy momentum tensor, the trace, is proportional to the mass. And since this is 0, you see this is 0, then the expectation value is equal to 0. Hadron masses will be all 0. Okay? It's a disaster, right? Proton is not 0. QCD has this symmetry, approximate symmetry, so the masses should be approximately equal to 0. But they are not. Why not? Because of quantum mechanics. When you want to make quantum mechanics, you have to introduce some parameter, what we call regularizing the theory. Okay? Because it has ultraviolet divergences, and you have to break this scale symmetry. Quantum mechanics requires that scale invariance is broken. Once you do that and play a little bit with the equations, you get that the hadron mass, the proton mass, is given by this. This F is like F min E. Okay, I just changed notation here. F min E is the gluons. In this limit, when we neglect the quark mass, they are so irrelevant. Let's neglect them. Okay? And then the mass of the proton comes from the expectation value of the gluon field. That is the explanation. Okay? So we know then that the quark the proton mass, the neutron mass comes from gluons. Okay? The entire mass comes from the gluon. Okay? Comes from this thing of the symmetry not being a symmetry of the classical symmetry, not being the symmetry of the quantum theory. Okay? It's an anomaly. And the anomaly is called the trace anomaly. There is where the mass comes from. But this doesn't help me very much. Okay? Why? Okay, a big deal, and what I do with that now is a good information for going to a bar, have some beer, and talk, impress people. Oh, the masses come from the gluons. Oh, yeah, nice. Yeah, but how? Exactly how it comes. That is our problem. And here I'm going to finish, essentially. Why is this interesting? Because this matrix element here, I can measure in the laboratory. That is interesting now. How I can measure it? Through a scattering experiment. I take one of these fancy particles. They don't exist here in nature, but I produce them in laboratory, which is called a quarkonion. A quarkonion is make a charm and an anti-charm. J psi, for example. It can be also a phi, S bar, and here is the proton. Okay? This interaction here is described, is giving me this expectation value. This I can measure in the laboratory. Not I, experimentalists. They can measure it in the laboratory. Then I have access to that matrix element. Then when I calculate it, when I make models to calculate that, I can understand what is happening there. Okay? So I have to be able now to construct theories, to construct models, to calculate this scattering. The experimentalists go to the lab, they measure, and that, looking at the scattering cross-section, at the scattering amplitude, you get that matrix element. Here, we calculate it make a model, and then we can compare, okay, my model describes that, and my model is based on this assumption. Oh, now I understand where the proton mass comes from. Got the picture? Okay. I cannot measure it directly. I have to use a scattering experiment like that. I have to convince people to put millions of dollars to make this experiment here. Okay? So I have a theory here. Okay, I don't have time. I leave the transparencies there. You can look. This is all my calculations. Okay, with a person in Spain. So it's very interesting because this force between the nucleon and the quarkonion is van der Waals force. And we can derive it. Okay, this is the van der Waals force. It's derived from chiral physics that you don't have no idea what is chiral physics, but it's the symmetry of the QCD Lagrangian and the trace anomaly. Trace anomaly you already know, you can impress people. Okay, now, so this calculation gives me the QCD van der Waals force. If I have a hydrogen atom here, another hydrogen atom here, okay, no charge, no charge. How can they interact? Van der Waals force, hydrogen bridges, pontes de hidrogênio, okay? Now, if I have a proton and I have a J psi, they interact through van der Waals force here, okay? It's made only from gluons. There are no quarks there, okay? Fine, I have to finish, okay? I'm just telling that this is not some theoretical fanciness. You can actually measure it in a laboratory, and actually was measured at JLab. Jefferson Lab is a laboratory in the United States, and they have measured this interaction. Okay, it's not good enough yet to compare with our calculation. You can measure it also at the LHC, and in particular, you can make femtoscopy is another subject we are working on, is to derive interactions, okay, from particles coming out from a heavy ion collision. This is called femtoscopy. We can so a heavy ion collision produces these particles, and then we detect them, and from this detection, I can tell about the interaction. It's another way to measure this. And this is crucial to understand the origin of the proton mass. Okay, I'm finishing. So this is another experiment that we want to convince people to do it. Is antiproton annihilation on the deuteron. Then you have the rescattering of J psi on the neutron here, and this is the interaction we need to understand. Okay? There is no calculation yet for that part here. This one we have. Okay, we can put this in a nucleus also. We have many papers on putting J psi inside the nucleus. Not to understand the nucleus, but to understand this interaction here. This gives me a clue on the proton mass. Okay, so what else are we doing in QCD? Okay, this is really the end now, okay? So in QED, you know that is atomic and molecular physics, okay? All that is a big field, atomic physics, molecular physics, pharmaceutical companies, and all that is biology. All this is this part of QED. Okay. QCD we also have. Okay, we have what is called hadronic physics and nuclear physics. Okay, this is like a molecule, and then you have here the atom, and here you have, this is the molecule, it's like the nucleus, and so on. Okay. We have QED, you have condensed matter. Water comes from quantum electrodynamics. Okay. So you have the phase diagram. In QCD we also have. Okay, this is explored now in heavy ion collisions. Okay, you have an ion, you collide another ion, and this is quarks. Then you produce this state called quark-gluon plasma. Okay. In astrophysics, QCD has a lot to do inside here. Okay, this you will have Horacio Nastasi talking about. Okay, is this holographic principle, is a recent development, and it seems to have some relevance for QCD. Okay? You will hear about that. Methods, what you use to calculate. You have numerical methods, is lattice QCD. Remember that computer that we cannot buy? Right? This is the big advance in the field. We poor guys, we don't have access to that. We have to collaborate with people abroad to have access to computer time. So the big progress in QCD will come from there. Okay? And the future. Is this a dead field? Actually not. Physics is experiments. If a branch of physics doesn't have experiments, it's not physics. I don't need to mention some fields in physics, right? They are not related to experiment. Some people believe only the beauty of the theory is enough for validating a theory. No, you need experiments. And there are many relativistic heavy ion collisions in the United States, the LHC, CERN, Europe, FAIR facilities, a new facility being built in Germany. Then you have JLab, United States. You have JPark in Japan, NIC in Russia to be constructed. You have BESS in China, the electron-ion collider that will be built in 10 years. You have projects for an international linear collider. This will be in 20, 30 years. Theory, numerical methods, lattice, stochastic methods to calculate, but these are numerics. Analytical methods are based on functional matters. And the challenges that we must understand is gluon matter, because only gluons gives you glue ball. Glue balls, bolas de grude. Yeah? These are things made only from gluons. Okay? We don't understand them. High density quark matter. Okay? This is very important for neutron stars. And it comes now with the gravitational waves. Two neutron stars colliding. This gives us information on the high density matter. Okay? You have dark matter and dark energy. Okay, now I'm forçando a barra. It might or might not have relevance QCD, but it might help that what we understand in QCD to use these concepts and prejudices to develop new theories for that. Okay? So if you are interested in a master or a thing, IFT has a place for you here, okay? And, you know, we have very bright people here, professors kind of clean and okay? And the infrastructure is good. Thank you. Sorry for being too late. Some people ask me about, I did not answer. Go to my office, okay, because there are so many that wrote to me, I did not have time to answer. Vão lá na minha sala e a gente conversa, certo?
Thank you so much again for the very didactic talk. I'm afraid we don't have much time for questions, but like he said, you can
I will be here.
For the professor. There are a bunch
Friday
of
afternoon, I will not be
too.
here, okay, but Friday morning, I might be here. Tomorrow for sure. Okay.
So thanks again, and we can go to a 30-minute break before we start the oral presentations.